Hello everybody, in this lecture we will be solving 1997 IMO problem number 3. Here is a view of this problem. We are given n real numbers and these numbers satisfy this nice condition here and also this one. We would like to show that there exists a permutation of our original numbers, real numbers, such that this final condition holds. Okay, so let me introduce a little bit of notation here to simplify all this mess. So first of all, let's call the original permutation as pi sub 0, I guess, x sub 1, s sub 2. So given this original permutation, we claim we can find another permutation. Let's just call it pi, y1, y2, and so on, such that they would satisfy this condition, right? So the interior of the absolute value, let me call it as s, or s of pi, because pi is this thing. So let also s of pi be equal to, let me just delete this part, be equal to y1 plus 2y2 and so on, and yn. So this one is s of pi. Okay. And well, yeah, why not? And also maybe because this expression n plus 1 over 2 here on the right hand side, I will just call it as r. It also shows up here on the right hand side as well, so that's also r. Okay, so a couple of things. So first of all, if this is pi 0, and look at this expression here, so let's just do it here. I will do the very common trick. So I will focus on the reverse permutation. So let's call the reverse permutation as pi of tilde. What I'm thinking of is this one. So that's the reverse permutation. And what's so interesting is, so if I calculate s of, let's do it here, or here probably, s of pi 0, and I add s of pi tilde to it, it's it's a very common trick, I guess. All right, so s of pi 0 would simply be equal to x1 plus 2x2 plus all the way to nxn plus similarly, so this one is s of pi 0. S of pi tilde would simply be equal to x sub n plus 2x sub n minus 1 and so on, all the way to x sub 1, nx sub 1. N times x sub 1 plus n times x sub 1. Now we just count the number of terms, so x1 here and nx1 here, so we will get n plus 1 x1 plus 2x2 here, and then n minus 1 here, so n minus 1 plus 2x2 and so on, and then n, and then nxn here, one more, so n plus 1 xn. So therefore s of pi 0 plus s of pi tilde is simply equal to n plus 1. Factor out that, so you'll get this expression here. And now if I take the absolute value of both sides, I will get this really handsome expression, and that's my first observation. So the absolute value of n plus 1 is just n plus 1 itself, because n is a positive number. And the absolute value of x1 plus all the way to xn is equal to simply 1, so that just vanishes, and so we have n plus 1 here. But recall that I decided to call n plus 1 over 2 as r, so that thing here is simply equal to 2r. Okay, so therefore, so that's a nice observation. Now let's focus on the following situation. So consider the case, so case 1, let's call it. Well, under the first case, if you look at s of pi 0, if s of pi 0 is less than, well, the absolute value of s of pi 0 is less than or equal to r, or the absolute value of pi tilde is less than or equal to r, then we're done. If then we are done. We are done. There's nothing to prove. So we have found the two permutations. So there exist permutations, and there they are. So therefore, oh shoot, this handwriting is not very good. Then we are done. Okay, then for the rest of this discussion, case 2, where we will simply assume, therefore, for the rest of this thing, that assume s of pi 0 in absolute value strictly greater than r, and s of pi tilde is strictly greater than r. But when you simply add those two, so we know that this sum is supposed to be equal to 2r. The only way this can happen is that s of pi 0 and s of pi tilde have opposite signs, right? Because if both of them are, let's say, strictly greater than r, then when we sum them, you will get something more than 2r or something like that, right? So what I'm saying is both of these should have opposite signs. So that's a crucial thing, right? So if you will, we can even say without loss of generality, if this is the real line, so this is 0, this is r minus r, and this is r. So we can assume one of them, let's say s of pi 0 is here, and then s of pi tilde is somewhere there. Okay, so now what I have in mind is the following. I claim that it is possible to start from pi 0, permutation pi 0, and then obtain from this permutation with successive terms, successive permutations, pi I plus 1, and eventually reach pi tilde, the reverse permutation, by simply interchanging two neighboring elements. So this is a slow procedure, obviously, but it works, right? So it is gradually you switch the terms and so on, right? So for instance, in the first case, for instance, when you move from pi 0 to pi 1, so for instance, pi 1, you can write it as x2, x1. So I just interchanged the first two components, right? x3, x4, and so on, xn. So in a similar way, you can define any way you want. x2, for instance, I don't know. So you can just find, well, we can, how about exchanging x1 and x3, right? So x2, x3, x1, x4. So I'm just interchanging two neighboring terms, and I continually do that. For instance, if I find pi 3, I'll get x3, x2. So this time I'm interchanging the second and the third, x1, x4, and xn. I think it's quite believable that this procedure will eventually, if you keep proceeding in this fashion, you should be eventually able to reach the reverse permutation xn all the way to x1 in this fashion. But why is this important, right? It's kind of useful to add some formality, so let me go ahead and add a little bit formal description of all this procedure, right? So this procedure can be defined nicely in the following terms. If, let's say that you have these two, pi I, so these are two successive permutations. So pi sub I, let's write it as y1 all the way to y sub n, and then pi I plus 1 is z1 all the way to zn. Then what I say is that there exists an index k in this range 1 all the way to n minus 1, such that z sub k is equal to y sub k plus 1, z sub k plus 1 is equal to y sub k, right? So all we do is the neighboring ones, we switch them, and z sub j is y sub j. Only two of the terms are switched, the neighboring terms, and the rest of the terms of the permutations, two successive permutations, remain the same for j not equal to k or k plus 1. So this would be a formal way to describe what we had in mind here. But then, now notice the difference between, so look at this this term here, pi I plus 1 minus s of pi I. If I evaluate them, remember the definition of s. S would just define like this. So if you have a permutation like this, then s of it would be just the sum, this weird sum. Okay, so therefore this would be equal to, well, all the terms will simply vanish, right, except the terms which are the consecutive ones, and so they will become like this: kz sub k plus k plus 1 z sub k plus 1 minus pi I, so we define this one here with these, so it would be minus k times yk minus k plus 1 times yk plus 1. Okay, and now yeah, so that should simply be equal to, if you just organize it carefully, so here we have kz sub k, but if z sub k was equal to yk plus 1, we have k yk plus 1 and minus k plus 1 yk plus 1, so we have minus y sub k plus 1 here, and then here each one here is equal to yk, so we have k plus 1 of it minus k of it, so therefore we have y sub k minus, and earlier we said there was one more here, plus y sub k plus 1 of it. But now using the well-known triangle inequality, so that would simply be less than or equal to this expression here. But recall earlier that we were given some bounds. Here are the bounds, so each of these are less than or equal to r, so this guy is less than or equal to r, that one is less than or equal to r, suggesting this guy is less than or equal to 2r. Now, so what's the point? So why have we done all this stuff? So what it means is that the distance, so this distance between two successive permutations, right? So, or between two successive sums of permutations, right, is less than or equal to 2r. But look, remember how we started early on. So without loss of generality, for instance, s sub pi sub 0 is less than minus r, and s of pi tilde is greater than r. So it is gonna make some jumps. So after each step, so let me write this down. So the successive numbers in the sequence s of s of pi sub 0, s of pi sub 1, s of pi sub 2, and so on. So these are some successive numbers starting from pi sub 0 all the way to pi, let's say, tilde, right? The distance between these successive numbers, the distance between these two and so on, they're all less than 2r, and so on, and then this one and the previous one less than or equal to 2r. So therefore, on the real line, our numbers will jump around. So if this is s of pi sub 0, so you will keep, sorry for that. So then we will make a jump, and then we will jump probably down, doesn't matter, then up, or down, well, something like this, up. But each time these jumps will be, in terms of size, would be less than or equal to 2r, right? But initially remember that s of pi sub 0 was less than minus r, and s of pi tilde is greater than plus r, so that's 0. So eventually, before we can reach this last guy, we need to make a jump inside this range, right? There's no way you can jump from here all the way to the outside to eventually reach this place, right? So eventually there must be a step where we jump inside this range, but once we jump inside this range, that's it. We have found the permutation which satisfy this desired condition, right? So yeah, it's a really simple procedure, very beautiful problem, and I hope you enjoyed it, and hope to see you guys in our next video.